right, let's get started. It's definitely pretty cold these days, so everybody stay warm. Have a couple more cold days, hopefully, then the temperature will be slightly better. So today we are at the end of week 11, okay? So next week, we're doing the checkpoint, project checkpoint meetings, okay? So if your team hasn't done so already, please have one of your team members go into Canvas, submit the survey, okay? So this is to help us to schedule the checkpoint meetings for next week, okay? So only one submission for each team, okay? So that way, it's easier for us to arrange the meetings. Also, so next week we're going to spend all the time for the for the meetings, so we cannot hold our regular office hours. If you need to talk to us the next week, please email us directly. If needed, we'll try to find a time. But next week it is going to be a little bit challenging to have a lot of flexibility in terms of when we can meet. Okay. The following week, we are going to, the plan is that we should have our midterm exam graded sometime next week, okay? So we'll post the grades, and then the following Tuesday, my plan is to return the exam copies, and we're going to discuss the midterm exam questions, okay? And also, if, make sure you check the homework questions and the grades. If there are any questions, please contact our TAs, okay? Another two reminders. So this is about what you need to submit, right, for the checkpoint, okay? So similar to our proposal meetings, so after the meeting, each team will submit your presentation slides and also your report, okay? So this will be just updated version of what you submitted for the proposal, right? Just highlighting, right, what you have done, what you have accomplished since the proposal, right? Now you hopefully have more details, right, of like specific questions you like to address or particular techniques you like to utilize, right? Or like some preliminary results, right? All those are good things to include, okay? Of course, it doesn't need to be, how to say, extensive, right? Really, we just want to see that there's some good progress, right? But also important to highlight is any challenges, any changes, or any adjustment, right, of either the scoping of the project or like say the scale, right, or the types of data you're going to use. So all of the things that we're trying to kind of like look at during the checkpoint meeting so that we can provide feedback, right, in time so that you still have time to incorporate that. And of course, this will hopefully help you to get to a success finish of your project. Okay, so look forward to hearing more about your projects next week. On Tuesday, we started talking about chapter 10, okay? So this is actually a new chapter in the 4th edition, right? So previous editions, we didn't have a dedicated chapter. But of course, now you have seen, right, deep learning has been widely successful in many application scenarios. And we have like mentioned that, well, we are not necessarily diving into all the technical details of all the different deep learning methods, but it's really thinking about how that would help us, right, from the data mining point of view, okay? So we started with some of the basic concepts, right? So from the very beginning, when people talk about neural networks, right, what is a neural network, right? What goes into the architecture, right? So very basic ones are what is a neuron, right? You're taking the input, you have those weights, right? You sum it up, and then you have some kind of activation function along with some kind of bias, so for you to decide the output, okay? But then for you to connect, right, from layers, right? The previous layer to the next layers, that's how a neural network is constructed. The key part is about training, right? How do you learn the parameters, right, in your neural network, okay? It is powerful, but you still need like very good data, and you need the computation capability to support all that, but also the newer, more advanced design, right, of the neural networks. Okay, so we talk about a few things in terms of when you're training your deep learning models, right? This is particularly when you have a lot of like parameters, and then you're trying to optimize, right? So we're talking about how you can find well, usually it's a local maximum, right? Like local optimal solution, but hopefully it gets close, right, to your global optimal. Okay, but then like with the gradient. Like descent algorithm, right? You can actually land at different areas, okay? But also there's the aspect about like generalization, because if you train your model where, right, and it gets very high, performance very well, meaning that very low error for the training set that may or may not translate to your testing set. Okay, so we're talking about the generalization aspect. Okay, so there are a few methods we'll talk about in terms of how you can improve the training process. Okay. And then we're going to kind of like talk a little bit, really not like a very detailed, but hopefully give you enough idea about what they do, some of the key characteristics, and how that may be useful, right, for data mining, particularly if you're working on some projects, right? Think about some of those may be applicable, okay? So there are, of course, different tools available, different libraries, so you don't necessarily need to like implement everything from scratch, but having good understanding, right, of the different characteristics and different capabilities, right, would help you when you're trying to determine whether this is something you like to utilize for your project. Okay, so at a high level, we're going to talk about there are 3 different types of neural networks, okay? Starting with convolutional neural network. So the term convolution is actually pretty simple, okay? All you're trying to do is that you're taking some kind of what do we call kernel, right? So you have your input data. Okay, so this is just a 1D scenario, okay? So you have your input data, you have some kind of function, so this is a kernel, okay? So you're applying this function, right, on your input, but with some kind of sliding window. So as you're sliding through, right, your input data, you're applying some calculation. So in this case, for example, like what I'm doing is that I'm taking 0.25, 0.5, 0.2, so basically you pick the current node and you look at the 2 neighboring ones, and trying to combine the value into one, right? So that calculation is really very simple. Once you do that, you have what we call a feature map. Okay, so that is about applying one kernel, right, to your input data. You get one feature map. Okay, of course, you can apply different types of kernels, and you would have different feature maps. Okay, so this is a 1D scenario. Okay, if you take a 2D one, similarly, right, all you need to do is basically define, right, what is the window. And within the window, you have this kernel function defined. So that you're applying, right, certain calculations, usually some kind of just weighted sum for your local region, okay? Of course, you can then generalize, right, to other dimensions. So once you have this notion, right, what you're trying to do is really about aggregating, right, some local information. And that is what the convolutions are trying to do, okay? But this has really motivated and empowered, okay, convolutional neural networks, which have been shown to be very, very successful, okay? So let's look at some of the core ideas, okay? So why is the convolutional neural net so useful, right? Starting point, right? This one is about this sparse interaction. Okay, so think about, right? So this is more like a traditional neural network, fully connected. Basically, if you remember our early discussion of the neural network, right? You basically have like your input layer. This, of course, in this case is 2D, but whatever you're looking at is that you're taking every value, right? All the input, right? It's a fully connected network, all right? This gets really, really dense, and the computation is really high, right? And then think about how you actually train this a model with that many links, okay? So this is about like 2 billion parameters for just actually pretty small, like 200 by 200 image, okay? So that's not what we want. Instead, we say, okay, can we actually have something that's like more localized, right? So that's the idea of the like sparse interaction. That means like we're only using those in a kind of more regional computation, right? So when I go from one layer to the next layer, I'm looking at certain regions, okay, at a certain granularity, okay? So in this case, right, so if you take an image and you can actually say like I'm using your kernel, the convolution calculations, right? You're looking at areas, right? So that you actually can see, right, compared to the fully connected version, already you have much fewer number of connections. And those connections, of course, like each connection is associated with some weight, right? You have to train, okay? And the other one is actually very important. It's about this parameter sharing, okay? Why is that important, right? Because generally, remember we're using the kernel, right, which is the convolution function we're trying to learn, right? So we're using actually all this information, but we're basically using this learned kernels, okay? So in a way, you're trying to learn the most effective convolution mechanism so that you can extract, right, the regional information, okay? Another thing that's particularly important, right, this actually particularly like how say it's evident when you look at the images, right? This is about the translation equivalent. Meaning that if you see a cat like to the left side, or cat to the like top right, or cat to the like another position, within your image, they all mean the same thing, right? So hopefully your convolution like process would pull out, right? Similar information, okay? That is also really powerful, right? Particular applicable, meaning that I see that in different settings, but I would still be able to recognize or extract information that is the most informative, okay? So that's really the high-level notion, right? And there has been, let me see, there has been a lot of success, right? But when you look at like a convolution neural network, right, what really goes into your network, right? This is generally, as I say, when you talk about neural network, you're talking about the architecture or the framework, right, of how the components are like combined together, right, in order to take from the input all the way to the output, and that also again will allow you to train your data, right? And even more like recently, people look at more of the explainable AI and the deep learning. They're actually trying to pull out information, right, from the parameters or the models you have learned, okay? But at a high level, when you look at like just the convolution layer, right, what it's doing convolutions, right? So every time we do the convolution in a way it's aggregation. I take a regional like a window, right? I apply my kernel, I get one value. So in a way, you're kind of reducing, right? The information you're leveraging, okay? But typically, right? So let me see this. Okay, so you would take, right, so you have like your original input, okay? And typically what I say, you will pick some kernels, right? We use multiple kernels because you're basically trying out different ways of calculating this, okay? And now that will give you the feature maps, right? Remember, like each kernel, after you do the mapping, you get one feature map. So if you have multiple kernels, you would have this kind of like a 3D version, right? Basically multiple feature maps, okay? So once you have that, right? So now you have this, of course, you still have your activation function, but then like there's actually very important things about this pooling, okay? You may have heard this term, okay? So pooling, again, is just a way of like aggregating, right? Like choosing information. So a lot of times that you can say if you do max pooling, that's simple, right? So in this case, if I do 2 by 2, okay? So 2 by 2 max pooling. So in this case, I basically take a 2 by 2 window, pick the maximum value. Very simple calculation, right? Or you can do mean pooling, okay? So mean value, of course, similar thing. You take 4 values, you take the mean. But what do you do once you do the 2 by 2? You're basically reducing, right, your dimensions by 2 on each dimensions, right? So like you start with a 4 by 4. After you do the 2 by 2 pooling, then you get 2 by 2. Right? Okay, so this is generally how you read, right, a design. So when people like show this kind of diagrams, you wouldn't be able to read, okay, what they're doing, right? And not in this one, maybe on a later slide, you actually have ways they will spare out the dimensions. So I mean, like if it's like a 2D, and then you may have multiple channels, then you have a way of reading, right? What's the original dimension after each convolution process, after the max pooling or pooling layer, right? Then you can see how the dimensions change, right? That's exactly like basically like how you're going to design your framework and how it'll be trained when you're done. Okay, so that's one convolution layer. So that means you take, right, the original one, apply the kernels, get the feature map, so you do some kind of activation function, and then you use the pooling layer. So that is the output of one like convolution layer. But that's usually not like in the real world, people actually apply multiple layers because each layer of convolution help you to extract information at a certain granularity, right? So if you can continue going, you actually can extract information that are useful at a different granularity, right? Think about images, right? So if you're looking at the very local ones, right? So you may be able to attract like a few kind of finer grained information, okay? But as you get like coarser granularity, your convolution actually may be able to extract some a bit of kind of like a broader patterns in your image, okay? So that's the high level idea. Okay, so typically, right, when people are using convolution neural networks, they have multiple layers, okay, multiple convolution layers, okay, and then towards the end, and then that is when you actually do a bit of like a fully connected, and then they have this kind of fine tuning to train the overall output, okay. So that's how you construct okay, the convolution neural network. Now, this is like a few examples, okay? Of course, like there are actually a lot more details. If you're interested, you can of course pick any of those like a classic convolutional neural networks that read some of the details, and they have more like specific in terms of how they design the different components, and they have evaluations, right? Especially those kind of ablation tests actually help you to understand like which components are like contributing at what kind of level, okay? But here, let's just look at a few examples, okay? So earlier we were saying that like if you have different levels, right, different convolution layers, they're actually extracting, right, different like granularity, right, information at different granularity, okay? So this is one example, right? So I have this input image, okay? I'm trying to, towards at the high level, I'm trying to predict, right, what types of objects it is, okay? So you could have cars, you have like bikes, or something else, right? So to extract that kind of information, what do I need, right? So my lower level, so this is more like the local, like starting with the raw data, which you have more of the individual pixels, right? And now you're doing more like the smaller region convolution. So you are getting a little bit like, as you can see, right, those are basic kind of like shape, well, not shapes, it's just like directional like patterns, okay? Maybe going in one direction, and in this case, you do a bit of kind of like grayscale, you're getting those kind of smaller patches, right? So if you just look at this, they don't really tell you much, right? You cannot tell this is a car or bike or something. But as you keep going, right, that's why I say if you like aggregating, right, because you go through multiple levels, right? So at each level of a convolution help you to kind of combine the information from a larger region, right? So as you go up further, now you actually can see a little bit, right? So you can see a little, this is more like a wheels, and then maybe the window, and the others I cannot really tell. But it's now you actually tend to see those pieces that are hopefully a little bit more semantically meaningful, okay? And when you combine them, that is how you can then identify, right, specific object classes. Okay, so there are actually a lot of examples of like how convolution neural networks can extract information at different granularities. So if you're interested, you can look up online. But this just gives you an idea why, like one, what does like a convolution like can do, but also why the different granularity is important, right, for you to have like multiple layers of a convolution. Okay, this is another example. This is also like give you a bit of kind of like a general sense. So your original, right, so you have this like input pixel. This is just individual pixels, right? So using the color term, so you basically say, this is really like, if it's RGB, you're talking about 3-channel, right, pixel level information, okay? Now, if you do like so one layer, second layer, of course, we're not looking at all the details, but this give you some idea about like now you're extracting, right, from the very basic, just kind of like patches, like of more of a finer granularity, and now you get into some of those shapes, right, that hopefully then give you a better sense of what kind of objects, right, cars, person, animal. So that is the higher level granularity or higher level information you're trying to capture. But that is really how, again, you're building up, right, the layer and by layer infrastructure for you to extract information. Okay, this is another point, as we mentioned earlier, is about like how like deep learning in many cases they can really help with the feature engineering, right? So I remember when I like started with, I think the earlier project I did for my PhD work was that we're actually trying to look for similar images. Okay, but how do you find similar images, right? So I remember we were working with computer vision like experts. So we're trying to look for like say image, for example, color patterns. Okay, so you're using some kind of like color histogram so that you see whether they have some similar distribution of the color pattern. Okay, but then also we're trying to extract some kind of texture information. So texture is about basically the let's say you're looking at some kind of gradient, okay, of the pixels. Okay, but also we're trying to extract a shape, right? Are there certain kind of directional, horizontal, or like a curved a shape? So it's a lot of kind of like, how to say, automated, but you need to kind of somehow pick, right, what kind of features you're trying to extract from your raw pixels. Okay, but with this process, right, the convolution process, this multi-layered design really allows us to automatically, right? You basically automatically kind of grouping information in many different ways, And then your training process, right, will actually now help you to identify which ones are most informative, right? So that you extract information that will become directly, right, meaningful for what you're trying to classify. Okay, so this is the third example. This is actually more concrete one. If you search online, you can probably find that there are actually a lot of I see a lot of tutorials or like coding based that you can actually just utilize and just play with the whole data set. Okay, this is actually a classic problem in machine learning. This is about like, this is handwritten digits. Okay, so number, I think they go from 0 to 9. Yeah, so basically just say, can you recognize, right? Or it's a classification problem, right? So you're being provided with this like handwritten like images, and your basis, okay, there are only like 10 digits, right? But you need to determine which ones. Of course, if it's a handwritten, you know, like we all write differently, or even the same person may write the same digit differently, right? So there's quite a bit of fuzziness in this like input data, okay? But turns out, right? The convolution neural network is really effective in terms of doing this, okay? So we'll not get into all the detail, but hopefully now this will give you a way of okay, how to take a like CNN architecture and trying to read it. Okay, what do we mean, right? Start with input layer. Okay, so as we said, right now you can spell out, right? What is your input dimension? Okay, so this is 28 by 28, so that means like basically is a horizontal. So this is like each pixel, right? 28 by 28, but it's only one dimension because here we're using grayscale. Right? If it's RGB, you get 3 like dimensions. Okay, all right. So that's my input. So each image, right, is 28 by 28 times 1. And now, first I do this 5 by 5 convolution. So the kernel, so they basically says that my kernel window is 5 by 5, right? And I do a sliding. So basically, I do like sliding window, right? So you can, as you can see, right, if it's a 28 by 28, if it's a 5 by 5, then that means that actually we'll be able to reduce it by 4. So that means 24 by 24. Okay, if you're not sure, you just try to do the sliding because that's basically the size of the window and also the dimension of your original image. Okay, so now you get 24 by 24. This N1, of course, this is basically depends on how many kernels you're using because that's, as I said, right, you can try different kernels, so you will get multiple feature maps. Okay, and then we have this pooling, right? So max pooling 2 by 2, so that means I'm taking every like 2 by 2 get 1 value, right? So that's basically effectively reducing your dimension, your dimensions by 2 from each side, okay? So originally I have 24 by 24, now I get 12 by 12, okay? That is one step, okay? But then I can do another round, right? Another 5 to 5, so now 22, but 12 by 2 then becomes 8 by 8, okay? And then I have, again, this is again, I can decide, right, how many kernels to apply. Again, 2 by 2, reducing down by 4 by 4. Okay, so once I have that, and then they have this kind of flattened, like a fully connected layer so that you can do the final tuning. But towards the end, you can take this, right? So this is basically the number of units, okay? So now you take this, right? So this is the whole network, okay? And then you have, of course, all the parameters along the way that you need to train in your process, okay? But this one, as I said, if you want to like search online, you can find actually a few code base. You can just play with it. I remember there was one that like say basically a very simple kind of like design like this would give you was a 98 or 99% accuracy, right? Very impressive. Okay, but there are of course a lot more continued research, but this is like the fundamental idea of convolution, right? How do you design your convolution layer? How do you have multiple layers? And also how this can be applicable in many settings. Okay, this is about convolution neural network, okay? And as you can see, it has been really powerful in terms of one-dimensional, two-dimensional like images. It's definitely a very good setting, all kinds of images, right? But then recurrent neural network, this one takes a quite different approach, okay? This one is designed for sequential data, okay? Sequential data means what? You have like, this could be time series. This could be some kind of like sequence of symbols, right? Or this could be text, right? So machine translation is another example, right? They actually look at the word by word, right? So that's a sequence, okay? So when you have this kind of data, and now you're trying to, of course, again, trying to extract, right, information from your data to understand what they mean. So you can do translation, you can do like a classification, okay, or prediction, right? So first starting point, okay? So when you look at the feed-forward network, that's the classic neural network design, right? What it's doing is that you from previous layer to the next layer, right? You have those hidden layers, okay? So what you're doing is you take the previous layer, right? The hidden layer, like h sub I minus 1. You take this weighted sum, right? You have a bias, you have activation function in order to arrive at the next hidden layer, right? Okay? But with RAN, okay, the important thing is that you are actually continuously feeding your historical information into the new data, okay? So one way to illustrate this is that, okay? So we have the input data, right? So this is like, say, different, like at a different word, right? You have one input. And then what we're doing here is that we take the hidden state, but every time, right, I'm applying the same, okay? So this is important, the recurrence part, okay? Same hidden to hidden weight matrix, that is the W, right? That's matrix, same matrix along the way, as you can see. Also, same input to hidden weight matrix, U. That means every time when I incorporate, right, new input, okay, same matrix here, and it's the same bias. So this alpha, A is also the same, okay? So this is about the recurrence. So that means, in a way, just like, I know I have sequential data coming in, right? But I'm kind of basically applying, I'm incorporating, right, the same type of information. So it's the same process of incorporating the new information, okay? So that way I can capture, right, the longer term, okay, sequential information, okay? That's a high level idea. Now let's look at how this is different, right? Earlier we said CNN can also incorporate one-dimensional data, right? My earlier example, right, how you do the convolution. Same thing, it's one-dimensional, and then you can just combine, right? So you do a sliding window. Every time you combine, right, the local window, the values in the local window get 1, okay? But how is that different from RNN? Okay, main thing, right, still is about the convolution versus recurrence, right? Because with my CNN, it's local, right? Because every time, I don't care about anything else. I only look at whatever is in the current window, right? There's really no, how to say, like, I'm not incorporating other windows at all, okay? Every convolution, current window, like take whatever values here, and I just calculate that one, okay? While with RNN, because of this like feeding like through, right, you actually have this long-term information. So everything's kind of incorporated in whatever the current state you're looking at. Make sense? Right? So that's the main difference, okay? Recurrence is really like you have this kind of sequential notion by design, okay? Knowing that whatever I'm looking at right now, I want to actually incorporate what I have seen before, okay? This is important, right? And let's see how this actually then like works in a more general setting, okay? So if you have some kind of sequential data, right, or like temporal information, okay, what you're trying to do is that, of course, I want to model, right? I want to model the whole like dimension, right, sequential time. So earlier, like I have shown that how the information is being incorporated, right? New information being incorporated, the historical information being incorporated, and like keep accumulating, right? You would also, like many times, you would add some kind of feedback loop, right? So that you can, whatever you have seen right now, you can actually feedback, right, to your earlier decision, because this is important. This is about actually training, right? We talk about like back propagation in a general neural network setting, because when you do the feed forward, right, using your current parameter setting, you can calculate, okay, if this is my current model, right, this model will give you this output. And then with this output, you go back and check, right, oh, this is not right, I need to make adjustments, right? So similarly, we need to do something like that, but now my back propagation is along the sequential dimension. Because remember, I have this sequence, right, that I'm trying to incorporate. So all the values or the errors I'm seeing is something that I'm trying to adjust as I go back in time or in sequence, okay? But this becomes challenging about this long-term dependency. What does it mean? If you have a reasonably shorter, right, distance, like a sentence, let's say, like with a few words, okay? You can probably kind of relate quickly in terms of like how the previous sentence, right, previous word, right, means something for what you're looking at right now, okay? But with RNA, as you kind of increase, right, the length of your sequence, okay, think about it, right? You're basically keep like adding information in, okay, and now at the end you see some kind of delta. That means that there's a difference, right, between the observed value and my computed value, okay. Now you're saying, okay, I need to go back and make adjustment, okay. So from the very current data, it's probably okay. You see a bigger delta. Remember, we're using the gradient, right? So the bigger delta would allow me to actually make adjustments. But once you go back a few steps, this delta or this gradient becomes very small, okay? When it's too small, now you don't even know how to make the adjustment, right? And that's why it's challenging. Again, we're looking at this gradient vanishing problem, okay? So because of that, right? This is actually a major challenge with the classic design of RNA, right? The idea of RNA is really nice, right? It's trying to capture sequential longer-term information, okay? It has been shown to be quite useful when you're talking about like shorter sequential information, okay? But when you have too long information, right? This will have this gradient vanishing problem, and also overall your model, right? Again, just becomes much more complicated, okay? So there have been a few improvements, okay, over the classic RNN design, okay? One approach is called a gated RNN. So that means instead of just incorporating everything uniformly, okay, I want to do something more adaptive, or I want to differentiate, right? So I want to do things differently, okay? So that's the gated approach. I mean, I'm controlling, right? To like what information is being continued, and what information being like forgotten, okay? Another one is attention, okay? So you may have heard about like transformer, BERT. So those are attention-based approaches, okay? So let's briefly talk about those ideas. Okay, so this one you may have heard in different settings. Okay, so RNN is a general, like a recurrent neural network that works well for sequential temporal information. But then, like I said, people realize that it's this kind of uniform application or incorporation of sequential information may not be very useful, right? It's not effective in many settings, okay? Especially when you have longer sentences, okay? So instead, people propose LSTM. This one is actually widely used, okay? If you're looking at some kind of like temporal data or sequential information in your project, definitely check out this one, okay? So it's called a long short-term memory, okay? At a high level, it's really about I want to differentiate or make changes, right, along the way. So instead of treating everything equally, I am using some kind of a control, okay, so that I can determine what information moves forward, what information should be forgotten, and also how I weight things differently, okay? So that's the high-level thing, okay? Let me actually use a blow-up version, right? So this is one cell in the LSTM design, okay? So similar things, you have the input, you have the hidden state, but the main idea is this one, the cell state, okay? So that means within my cell, I'm trying to decide, okay? So here, I have my input, right? So earlier with RNN, you just, you give me the input. I basically have a standard way of using I have the U matrix, I have the W matrix, right? That's how I take that and the bias so that I would have, right, apply the same process, okay? But now we actually have per a cell. So that means that for every input point, I have a way of deciding, okay? From the historical information, what I remember, what I keep versus what I forget, okay? Think about your stock price, right? Think about a weather forecaster. Think about whatever, or the sentences we're talking about, right? So you're trying to decide, right, how much I remember, how much I forget. Okay, that's really the idea, okay? So you would have this, we have this 3 control gates, okay? This one is the kind of like F for forget gate, okay? So that means how much you would forget, right? So you have the current, or this is actually the previous layer, hidden layer, right? The information. So how much you would forget, okay? How much to keep, okay? And then this is then how you would generate the next layer for your hidden state, okay? So that's just one, right? But because I have these 3 control gates, okay, those are the kind of control functions, right? That I now have a way of adapting, right, in different settings. Because there may be scenarios that, hey, I really don't need anything that happened last week, right? Or like for any, like in my particular setting, I don't need, like if you look at the sentences or paragraphs, right? I don't need like something that like occurred in the previous paragraph. Maybe not as relevant, right? But all those need to be adapted to your data set for your particular problem, right? So that's why with this kind of control, now you have a way of incorporating that information. Okay. As one example, we actually use our LSTM successfully for a problem in terms of predicting ozone concentration. Okay. So if you look at the ozone, it's impacted by many things, but a major factor is the traffic, right? So I think we did this in LA. So the traffic patterns is actually quite different, right? Changes dramatically during rush hour versus weekday, weekend, and also like wind speed, for example, wind direction. So all those are different factors, but they impact your prediction at a different granularity, okay? So we were able to use LSTM to actually really be able to capture, right, the impact at a different scale. And if from the temporal setting, right, I don't look at the last, say, 24-hour or 6-hour like uniformly. Rather, I'm looking at like how things can be more impactful versus less important using my training data. So I was able to actually train models, right, that actually would then give you specific, right, those gated control of what information to incorporate. Okay, so that's LSTM. Another one related is actually, we said this is GRU or GRN. So the other one is just general gated, so that means they don't have all the specific ones, but really they have just 2 gates, right? One is about what to remember, what to forget, similarly, okay? But ultimately with this idea is that because you're trying to incorporate, right, this longer term information, the key thing is about, like, what do you forget? What do you remember? Okay. All right. Another one, also quickly. This is about the attention mechanism. Okay. Attention actually has been used more increasingly, more in many of the deep learning like architectures. Okay. And people have shown that that is really useful. Okay. So let's look at this from our like recurrent neural network setting. Okay. So in the like classical design, right? Traditional RNN, as we have said, right? It's a recurrence, right? But it's uniform, right? Uniform incorporation of all the information. Okay. So what we're doing is that we take the entire source sentence, right? And I would like feed that all, everything's incorporated, and then have my one summary vector. That's how I'm doing it, right? With the standard RNN. Okay. Because of that, right? Oh, this is actually, I'm sorry, I should have mentioned that this is for actually machine translation, okay? So you have sentences in the original language, and then you're trying to translate, right, to a foreign language, okay? So basically, we're talking about like 2 RNNs, right? The first one is that you're building this for the source language, okay? So you're incorporating the information, you're providing some summary, and then like you're trying to like use this, right, for your destination language. So that's another RNN, okay? So the question is that when you do this in a kind of uniform way, right, the inference of the summary vector decreases, okay, as the second RNN progresses, because as you can see, right, it's a uniform recurrence, uniform incorporation. So when you have more and more sentences, right, or when you take the first language, the sentence in the first language, and now you're kind of progressing with your translation, the second one, now you actually see smaller inference, okay, from the previous part, okay? But think about translation, right? When you're translating something from one language to another one, okay? Best case, 1-to-1 mapping, okay? Every word in the original language, in the same order, translate, right, to like the next one, okay? So if I'm saying like this is an apple, okay? I don't know another language, right? But you may have almost a direct like 1-to-1 mapping. Great, right? So that is good, right? But in the real world, right, most of the times they're not one-to-one translation. Instead, right, you're trying to figure out, okay, for this particular word, okay, or this particular position, okay, which ones are more impactful, or which are the contexts I really need for this particular one, okay? So this is what we're trying to do is that for the second, right, RNN, we're adding this, what we call a context vector, okay? So context vector, in the simple case, it's just a one-to-one mapping, right? I only look at, like, say, currently I'm in position 5. I only look at position 5 in the, previous, in the source language, okay? But maybe not, right? So now your training is, okay, no, don't just look 5. Maybe you want to look at, position 1 and 2 and maybe 6, right? So that just give you a sense of, what you should pay attention to when you're trying to make the translation, okay? So all we're trying to do, right, so really we're just adding this, right? But this turns out to be very useful. As I said, right, this earlier, you're basically kind of blindly incorporating all the information, right? And when you have longer sentences, you're actually really losing a lot of the key information, okay? But with this context or this attention mechanism, you have a way of kind of identifying ones that are most relevant. Okay, so this is what we're trying to capture, right? C sub j, so that's basically for position j, right? This context vector attends to most relevant hidden states in the first RNN. So that means those are the nodes that are most useful or informative I should pull out when I'm trying to do the translation, right, for the destination language. Okay, this is really a very high-level introduction of the attention mechanism, but that's really the fundamental notion is about instead of looking at all the information, the accumulated information, right, in a kind of uniform way, the attention mechanism or this vector help us to train and pull out places that are of particular importance. Okay, again, using my earlier ozone prediction example, right? We also use the attention mechanism, but once it just intuitively just okay, if I want to look at predict, right, the ozone concentration for today, okay? Of course, I want to look at the previous days, right? But it's probably more important for me to look at a time, the contexts that are more similar. For example, rush hour, right? This is, again, a rush hour time. It's probably quite different. Or if I'm looking at right now, today is windy. I have a northwest wind at a certain speed. So now I'm paying more attention to the wind direction or the wind speed, right? So again, those are things that are helping me, right? Instead of looking at all the past, say we had a pretty long time duration, right? But the idea is if you look at 24 hours right ahead, in the past, now you have something to differentiate or paying special attention to things that are more relevant for your current state. Okay, so hopefully that gives you some idea, right, of the recurrent neural network. Okay, one more category we're going to talk briefly. This is about graph neural networks. Okay, so convolutional, actually used for 1D, 2D, actually 2D most of the time, right? Recurrent, particularly useful for sequential temporal information, okay? Graph neural network, as the name suggests, right? We're looking at some kind of graphs or networks, okay? So either this is a physical network, right, graph, or as I said, graph can be really powerful. You just kind of use that as some kind of abstraction of entities and relationships, okay? So with high level, right, what we're doing with graph is that we're trying to learn some kind of representation, okay? This can be done for the node level. So that means I have, for example, a social network, right, of individual people, okay, or accounts, okay? So within the social network, of course, you can see, right, individually, I have my, people I'm following, people that are following me, okay? Or I post things that people may have interacted with me, right? Or people may have forwarded or liked something. So those are the kind of information you can capture, right, in the graph, okay? But now if you're trying to, somehow represent individual nodes, what information do you use, right? So you need to figure out what kind of ways. In the kind of manual feature engineering, say, okay, how many friends do you have, or how many followers, how many followers, how many posts, or what kind of posts you have, or who are following you, or the kind of things, right? There are a lot of stuff, okay? So using this kind of deep learning approach, people have shown that it actually can be really powerful in terms of learning effective representations, okay? Both for the node level representation and the graph level representation, okay? So if you look at like one social network, you maybe look at individual nodes, or if you look at different types of graphs. So for example, like the pharmaceutical companies, right? They're really interested in kind of different interactions, right? So they actually look at like various kinds of graphs about how things like link to each other and how they react in different settings. So now you may be very like important for you to be able to characterize, right, or learning features about those graphs so that you have a way of classifying or making predictions, okay? So think about some of the application scenarios. You may be able to do node classification, right, with the representation. You can do link prediction. That's actually very important, right? You can actually now predict. This actually, you may have seen some of those, like people make recommendations, right? You may recommend, say, oh, you actually may want to link with this person, right? Or you may want to kind of reach out to this, or I say, oh, you're likely to watch this, you're likely to purchase this, right? So those kind of link prediction is useful for various kinds of recommendation strategies, okay? And also, like, say if you have a lot of networks, of course, this is a mining process. That's, again, why we care about, right? Some of the graph like mining is that graph neural networks can be really useful for us to pull out patterns, right? Both normal pattern or like unusual patterns from graphs. Question is that how do we do it, right? So again, think about like convolutional neural networks, right? Because we said earlier, right, you have the graphs, so you can apply some kind of kernel, some kind of window, you can do the convolution. Can we do that for graphs? Okay. If you just do this in a direct way, no, right? Because, well, when you look at your 2D or 1D, right, this is actually a very nice fixed structure, okay? So you can easily take your sliding window and like go through it to calculate your convolution values, okay? But with graphs, right, you cannot say, okay, you take this node, how do you define your window, right? That's one thing, because you actually usually you don't have a fixed size, right? You cannot say, I take this node, I pick the neighboring, like say 4 by 4, 3 by 3, then to do some kind of aggregation, okay? Because all the graphs are different, all the vertices are different, okay? So you cannot use this directly, okay? And also, right, this is actually also important, right? Earlier, when you do this kind of sliding window, right, the values within your window, they have a certain structure, okay? But with the graphs, right, a lot of times you can rotate things, right? And they will still be the same thing. They will look quite different, right, if you just visualize it, but they really mean the same graph, right? So that is also another property, right, that is unique to graphs, right, that again makes it not like directly applicable for CNN, okay? Another thing, right, earlier we talked about like translations, right? So when you have this cat, right, here versus there on the image, doesn't matter, right? I can still capture it, right? But you cannot take a subgraph, right, here from a graph and then just shift it to another area. So the graph, depending where they are within the bigger graph, right, they may mean very different things, okay? So again, this is something that like just makes it not possible, or you cannot like just directly apply a CNN on your graph calculation, okay? So let's do something that's more specific to graphs. Okay, so this is a general idea of it's still convolution, right? But we're doing this on a graph. Okay, so now we're trying to utilize some characteristics of the graphs when we're trying to define our convolution process, okay? So there are different ways to do it. At the top level, they're like either spectral convolution or spatial convolution. So spatial convolution basically trying to translate, okay, your graph into the spectral domain, okay? So I think earlier we mentioned like Fourier transform, wavelet transform, right? So something similar. So this is actually like Laplacian matrix, okay? This basically is a way of capturing, right, how the graph, right, changes, okay, or the relationships of the different vertices and their connections, okay? I'll skip a lot of detail. The textbook has more detailed discussion, and you can probably follow the structure or read a paper on the actual process. But at a high level, what are we trying to do? Okay, So again, we're comparing with a standard, right, feed-forward neural network. Standard one, right? Standard, you take this one and you get a hidden layer, hidden layer, hidden layer, that kind of thing, right? But with the graph convolution, we are adding this matrix, right? So this is our like Laplacian matrix, okay? That is basically, how to say, that's the convolution we're trying to do, okay? So we're basically doing this at the whole graph level, okay? But we're basically saying how you actually transform, right? The graph matrix, okay? From one layer to another layer, okay? In a way, this convolution process is trying to capture the relationship, right? Because ultimately with the graph, right, at the matrix level, the values in the matrix is basically talking about, okay, this node is connected to that, like is important for the other node. So like to calculate your convolution, you say, okay, I want to grab those nodes, right? And then combine some kind of value. This could be mean, could be average, or whatever. And then combine that to compute the next layer for my graph, okay? So this matrix is really a way of capturing this global kind of connections or relationships, okay, in a weighted form, in a convolution form, so that you can arrive at the next layer for the impact of different vertices on other vertices within the graph, okay? That's a high-level idea for the spectral convolution. But there are many different ways of computing that, right? Another one, spatial convolution. This one is a little bit more easier to visualize or straightforward, to understand. But what it's doing is that you have this kind of neighborhood notion, right? I can visualize my graph, and I know who I'm connected to, okay? So instead of looking at the whole graph, okay, I'm basically looking at my neighborhood, okay? So I can start with my one-hop neighborhood. That's easy, right? Whoever is directly connected to me. Or you can do two hops, k-hops, right? So that is how you define your local neighborhood. Okay, so that's one notion. Okay, so that's why it's spatial, right? When you have this neighborhood, also you can add in this notion of a messaging passing. In a way, just more about being connected, right? One-step connection, two-step connection. Okay, so we have talked about 6 degrees of separation. That means how are you connected to any node, right, in the graph. Okay, but so the message passing is a way of saying, okay, whether you're connected by one hop or within one hop or two hops or three hops. Okay, so this is also a gradual process for you to determine, right, how from let's say initial node, right. So A is my target node. Now you're trying to look at one hop neighborhood, two hop neighborhood, but general idea is that, okay, like any other node, right, for them to connect to A, right, how are they connected? So that's the messaging passing piece we're talking about, right? So at the very beginning, I think, for example, like AC, AB, EF, I'm trying to capture, like EF actually has to be connected through C, okay? So at the very beginning, B, C, D, those are the ones that are one hop away from me, right? So A will be kind of connected to BCD only within a hop, okay? But when you get to two hops, now you can see, right? So through B, I can actually get to C, right? So that actually both A and C will be connected here. But for interest is here, right? For C, now E and F are reachable to A, okay? So that's how you kind of gradually, again, expand. But this is more of a local, like a neighborhood view, versus the spectral one is more like the global graph relationship. Okay, all right. Very different approaches, but at a high level, what we're saying is that, okay, yes, we're doing convolution, but our convolution process needs to be designed, right, specifically for your graph, and especially what you're trying to capture in terms of property of your graphs. Okay, so if you're talking about how information progress, right? For example, in social media, always people talk about, okay, whether this become viral or not. Okay. That depends on who's starting it, right? And who are connected to this person, what content it is, okay, when this was posted, and how people reacted in the earlier steps, okay? All those will be information you can try to capture, but this kind of convolution process, right, out of the graph layer could be what we're looking for in order to capture, right, the contributions of individual links and individual vertices. All right, that kind of ends our discussion of chapter 10, okay? This is deep learning. Deep learning is actually a very active field. A lot of things are happening. As I said, we're really using one chapter And we're not even covering all the details within the chapter, okay? But hopefully this gives you a reasonable understanding of what is a neural network, right? What is a deep learning? What are the different architectures? What are the things you need to pay attention to when you're using, right, deep learning for like related problems, okay? So one, just understand generally what they have, like people have been used successfully in different settings, but more like kind of connecting specifically to your course projects, right? Definitely think about, right, how this can be useful. I know like sometimes those kind of neural networks seems quite complicated, but as I said, right, there are a lot of tools, right? And there are online like playground, right? We use that neural net playground. Actually, they are, I would say, reasonably easy to get started, right? Like you don't need to like, how to say, do everything from scratch, right? There are a lot of kind of readily available tools, or with a simple modification, you can apply it on your data set, okay? So that's definitely like, if you have time, right? Definitely like something like interesting to explore, okay? But just like keep in mind, right, as you're trying this, right, knowing that neural networks usually, one, require a lot of data, okay? The training process can be like quite intensive, right? Computation-wise is also hard, so that's why I say when you're trying things out, right, try it, but do your reasoning about, do you expect this to work, or it doesn't work well, or worked well, right? Like trying to learn from that process and see like whether that helps you to deepen your understanding and maybe hopefully, right, provide some useful results for your project. Okay, with that, I'm going to move on. That's the next core chapter, like technical chapter. Okay, this is about outlier analysis. Okay, so starting from chapter 4, right? Chapter 4, chapter 5, we're talking about pattern mining. Chapter 6 and 7, classification, and then we're talking about the clustering. We'll talk about deep learning, right? So all those are, of course, a lot of kind of fundamental techniques. Okay. Outlier is also very, very useful, particularly for data mining, okay? So that's why we have a dedicated chapter. We are going to dive into, okay, some of the general understanding, right? Starting point, of course, like why do we care about outliers? What are they? How do we find outliers, okay? Starting point, okay? So I have used this kind of fraud and transaction, right, quite a bit. Especially remember we were talking about like false positive, false negatives, right? And also like how you can like, is it more important for you to flag something that is like, or is it worse for you to flag something that wasn't a fraud, or it's worse for you to miss out something that was actually frauded, right? But here, let's just look at this as like if you are now actually sitting down, right, to design a method to detect those kind of suspicious activities, okay? So the setting is that you're monitoring transactions, right? A lot of transactions. The credit card transactions happen very quickly. There are many of them. So at any moment, you're looking at this like a stream of transaction come in. You need to react very quickly, right? The satellite with streaming data, usually you don't get to say, oh, hold on, let me look at historical data. But by the time you finish looking at that, now you have more data you need to work with, right? So you need to keep up, right? Keep up with the stream that's coming in, and you need to make decisions very quickly. Okay, but what are something you're trying to look for, right? What do you mean this is suspicious, like transaction, okay? So the general notion is that, okay, suspicious means that this is unexpected, right? Okay, so if you look at a normal transaction, okay, so like say, typically my users are very different, very diverse, right? They buy things very different. So their usage behavior already very different, okay? So I don't have like one uniform pattern. Instead of say, okay, I know my users are very diverse, but they still have some kind of expected pattern, okay? And then something beyond that would be like if that doesn't happen like regularly, would be something suspicious, okay? Earlier days, people had a more maybe simple examples, like if there's a, well, all of a sudden you see somebody like purchasing, I'll say $10,000 of stuff, right? Even though my regular day is just like a smaller item, grocery shopping kind of thing, right? That can be suspicious, right? Or this could be actually legitimate, like purchase, but that's rare, right? So that's usually one way to flag it as, hey, this is different, okay? And this one is also interesting, right? So like a multiple on-site transactions within 10 minutes in 2 locations that are hundreds of miles away, okay? So this is just more like by physical like limitations, right? If you're assuming this card belongs to one person, and this person is actually doing like in person, that's also important, right? If it's online purchase, they can be anywhere, right? But if it's a physical, it means, oh, they actually did a point of sale here and a point of sale there, but they're so like, they happen to quick like next to each other, but then these locations are far. That's one, of course, more definite like a scenario. But that's harder to find, right? Nowadays, like the scammers are also really smart, right? They have different ways of doing different things, okay? And data patterns are changing. That's why outlier detection is not easy, right? Because outliers usually means that you don't have a predefined way of saying this is an outlier. Rather just say, I see what is normal, and I see something that's different, okay? And there's a lot of like fuzziness to it, okay? So even though the notion is simple, right? Say most of transactions are normal and only a very few are normal, that's hard, right? But also, yeah, I have a lot of normal pattern, great, right? But how do you abstract your normal pattern so that you can say this is quite different from my normal pattern, okay? So that's a hell of an idea, okay? So typically when we say outlier detection, right, sometimes referred to as anomaly detection or like finding anomalies or outliers, right? So you want to find data objects, okay, whose behaviors are quite different from the expected behavior. That's very vague, right? Intuitively makes sense, right? Something that just looks very different, okay? But to have a more like a concrete design, like definition of this is hard, right? For any different pattern, like there are many different real-world scenarios, and the pattern could be really different. So that's hard, okay? But outlier analysis actually have been very, very important, okay? Useful, important, and actually increasingly important in many ways, okay? Nowadays, right, especially, right, so you say there are something that's just critical, right? You need to know there's kind of like a security breach, okay? This is something like, of course, like fraudulent transactions, okay? This would be kind of like insurance like fraud, or like if you look at like important machineries, right? If things are about to break or things have broken down, right? So you want to be able to detect those, okay? And usually you need to detect this in a timely fashion, okay? And going back to the earlier point, this is rare, right? So you're really looking for a needle, right? Or a few needles in a haystack, right? And things change over time because the other end, right? Usually the attackers, they're smart too, right? They're trying to utilize whatever the advanced technology they can get on. So it's a very difficult like problem, but it's important and increasingly important. Another thing I really want to highlight, when we talk about outliers, don't always think as bad things, right? Outliers, yeah, they can be errors, they can be kind of like a security breach or just bad behavior. But many times, right, that's why I put the scientific discovery, right? Scientists, a lot of times they're looking for the outliers, rare patterns, because that's usually something of significance. Okay, so when you're looking for outlier, don't always think it's just like bad, right? For example, like the Large Hadron Collider, right, that's running in CERN, they're generating a lot of data. Every time they do experiment, they generate a lot of data, but majority of the data would not be that useful. They're really looking for those rare occurrences of certain scenarios. So just keep that in mind, right? Outliers is important, but they can mean very different things in different settings. Okay, so here let's kind of try to talk about the difference between outlier detection and clustering. We'll see later that clustering is actually heavily used for outliers. Because you think about it, right? When we talk about outlier, like clusters, what are clusters, right? Clusters are objects that they're kind of next to each other. They're similar to each other, right? And they're different from others. Okay, so that's good, right? So with that notion, you can say, actually, I can use the clusters, because the clusters represent those major or majority patterns, right? Because to form a cluster, you need to have enough objects. They're similar to each other. That's a cluster, right? Okay, while with outliers, of course, I'm looking for the minority, right? Things are not belonging to those major groups. Okay, things that are different. Okay, so in a way, you could actually say that if I have a way of identifying those clusters and I identify those major patterns, right, then I have a way to identify ones that don't belong to those clusters, okay? So those are the exceptional cases, right? Because since they don't belong to clusters, okay, I can identify them as outliers. So you can see, right, they're different, but they can be quite relevant to each other, okay? But another thing is about supervision, right? Remember, like clustering is unsupervised, right? So generally with the clients will say, yeah, we're not providing a label, we're not providing a training set, you're really just being provided with the objects. And you're trying to decide, right, whether they're clusters or not, or who belongs to which clusters, okay? But with outliers, right, we say, yeah, you can use clusters to find outliers, but outliers can also leverage supervision, meaning that you could have labeled data saying that this is outlier, that's not an outlier, this is outlier, that's not, right? So that kind of supervision, okay, is something you can really leverage, right? And actually can be really powerful for outlier detection, okay? So they're related, but think about how they're related but different, okay? Now, let's dive into the specific definition and then really get to the point about how we actually find outliers, okay? So outliers at a high level, right, it's basically just say something that's different, okay? So we can define outliers as objects that are just that deviate, right, from the expected behavior, okay? Of course, how do you define, right? Like, what is the expected behavior, right? And also, how do you say that is significantly? Like, how do you measure, right? This is different enough, okay? So sometimes we use this notion about like whether you have some kind of underlying mechanism. That's what I say, if it's a fraudulent activity versus a regular purchase behavior, right? The underlying mechanism is different, okay? As a result, you will see something, right, that behaves quite differently, okay? Also, there's some notion here, right? Outlier versus noise. So are outliers noise? Like, do we just find outliers, oh, those are just noise, we can ignore them? Hopefully not, right? We already gave examples, right? This could be fraudulent activities. This could be significant scientific phenomena we're looking for, right? So some of the outliers may actually turn out to be noise, right? Just the fuzziness of nature, that is fine, right? But a lot of times you may find outliers are more significant, okay? So that's one, okay? Another one is outlier detection versus a novelty detection. What does it mean? So novelty, people just usually mean that there's an emerging thing. For example, deep learning, right? Deep learning was like not around, right? Like a decade back. Okay, but then nowadays it's a norm. Okay, so when deep learning was just starting, okay, that would be considered as an outlier because everybody was talking about maybe like support vector machine. People were talking about a decision tree, and now you're starting talking about deep learning. So deep learning was considered outlier, right? It's different, and it's the minority. Okay, so that's at the beginning stage. Okay, but over time, novelty really means that it will become the mainstream, right? So nowadays, deep learning is one of the majority patterns, right? So it's no longer outlier. I mean, that's now the mainstream, right? So novelty detection and outlier detection are related, especially at the beginning, when something was just starting, right? It will be seen as outlier, okay? Over time, becomes more like dominant, and then, of course, then it's no longer outlier. Okay, but these two are, of course, also quite related, even though they mean kind of different things. Okay, but you can use outlier detection, right, for earlier detection of novelty. But then you need to kind of monitor those outliers to see whether it becomes actual novelty or just a noise, and it goes away. Okay, all right. There are actually different types of outliers. Okay, you can say, oh yeah, you already said outliers. They're just different, right? Objects that are different from the rest of the other objects. But there are actually different types of outliers, okay? The simple one is what we call global outliers, okay? Sometimes it's called like point anomaly, okay? That's just saying, okay, yeah, when you look at this point, you already know it's so different from the others. That's a single point, right? Okay, so you just look at one value, say this is an outlier. Okay, great, right? So this could be like I don't know, temperature, precipitation, the ozone concentration we get, whatever. But quickly people realize that, hey, many times I cannot decide whether this is an outlier just by itself. I actually need to understand the context, okay? So for example, like we just had how many, 7 inches of snow or probably more accumulated now, right? So you say, okay, 7 inches of snow in one day. Is that an anomaly? Would you say it's a yes or no? You probably need to ask where, right? Okay, this is in Boulder, this is in November, yeah, maybe. But if this is like 7 inches of snow in one day, this is in Florida in June, let's say, right? As you can see, right, all these are relative, right? You need to know the context, okay? So this is actually the more of the majority. Whenever, like many times when you're looking for outliers, you need to understand the context because a lot of times it's relative, right? So if you say, oh, it took me 30 minutes to commute today, okay? Is that an outlier? You probably need to ask, where do you live, right? What does it normally take, right? Okay? So all those kind of things, right? You don't look at it. So in the global outlier, that one is a simple case, right? Sometimes you can do that, but many times you will need to look at the conditions, okay? Under what kind of conditions that this may be considered outlier, okay? The next type is even more interesting or complex, okay? So this one, right? So you say, okay, instead of just saying individual object being outlier or not, we're actually saying, hey, if you just look at one object, I cannot really decide, right? Like for example, like if you're traveling, say, okay, I see one flight being delayed out of the Denver airport, okay? So if you look at the Denver airport, say, yeah, one flight, no, that's a typical, right? It's kind of expected, right? But all of a sudden, you see 100 flights being delayed, okay? That says something, right? So in this case, individually, right, each flight doesn't really count as outlier, okay? It's the collective set, right? Because there are so many of them happening together, okay? And now you say, hey, something's happening, right? This is unusual, okay? So as you can see, right, those are all outliers, but they happen at very different settings. Okay, so again, if you're like thinking about outlier analysis for your project, right, try to leverage this information. Okay, do a bit of reasoning. Okay, what is an outlier? Is this like contextual outlier, or this is like global outlier, or collective? Okay, all right. Now let's talk about. Yes, we know we have different types of outliers. We know that it's useful. How do we find it, right? Because sometimes when you see an outlier, once you have find it, it's actually easier to say, yeah, this is an outlier, or say, no, it's not, right? But to be able to identify that one is hard, okay? So there are a few challenges to it, okay? First, right, we already said, right, for you to say this is an outlier, you say, okay, what is a normal behavior, okay? What is a normal versus outlier, okay? Sometimes it's just hard for you to be able to model either the outlier behavior directly or the normal behavior, right? All this are like, even for the normal behavior, there are so many types of the normal behaviors, right? Your customers can be so diverse. So that's one thing, right? You just say, how do you even find a good way to model them, okay? Other one, right? Application specific, right? Already said, right, the different outliers and the outliers can be quite different depending what kind of application scenarios you're talking about, right? So there's a lot of kind of application specific notions of what is outlier, okay? Especially you're talking about a context, you're talking about the collective ones, you really need to know what kind of context, right? What kind of attributes you're utilizing based on your application to say that, hey, this is something that I'm watching out, and if they are different along those attributes, that could be outlier, but those attributes don't really matter, right? Another one, noise, right? Earlier we mentioned, right, there are noise everywhere, but noise is a particular challenge for outlier detection, right? This actually relates to like earlier, remember we're talking about support vector machine, right? Why we're trying to look for the margin, right? The larger margin. That is because, yeah, there are noises, right? If you have a bigger margin, you have a better separation, right, of the different classes. So it's easier to make the separation, okay? Similarly, outliers, right? If you have normal behavior, you have outliers. If there's a clear separation, great, right? You can separate them, done. But many times the noises, that means your normal behavior can have noises, your outliers can have noises. This actually may blur the boundary. Okay, so you don't have as much separation. Okay, I think I have one more point finish before I finish here. Interpretability, because ultimately when you say this is an outlier, come on, you need to explain, right? Why this is an outlier? If you give them a list, say, oh, this is a fraudulent transaction. Why? Right? Can explain, right? How it is, like how you can actually measure, like the degree of outlier. So just say some way of saying this is indeed outlier and why it is. Okay, we're out of time, so we'll stop here. Reminder, next week we're doing the checkpoint meetings. Make sure you finish the survey, and we'll be talking to you next week about your projects. Okay, thanks everyone. Take care. Yeah, sure.